Hi everybody. We're moving on to the second theory family that we're going to take a look at in this course. We started with behaviorism, looking at people like Pavlov and Watson and Skinner, who basically saw people as very, very similar to animals. Rats and pigeons specifically were what they did most of their experiments with. And now we're moving on to information processing, which was the beginnings of what we now call cognitive science. I wanted to get you some history of the time period here that's not in your chapter. Basically, behaviorism ruled between 1900 and 1950. There was no serious contender for scientific psychology. If you trained in cognitive psychology, you trained as a behaviorist. And in fact, that went on for quite a time after that. But what happened in the 1950s is now known as the cognitive revolution. And there were a number of things that happened. Basically, one of the big things that changed things were computers. And in 1950, Alan Turing, who's known as the father of modern computing, wrote the first computerized chess program, the first program that would allow a computer to play chess. Ironically, he wrote it before there was a computer that could be programmed in this way. So the only known chess game played by this program, he played himself, acting as a CPU and following all the algorithms he had written out in his chess program. Turing was a brilliant man responsible for very much of what we see even today in modern computers. He invented the ideas of algorithms and the whole idea that thought could be modeled by computers was his passion, was his obsession practically. And so for the very first time, if a computer could do something as complex as playing chess, there was hope. Psychologists had some hope that it would be possible to open that black box that Skinner talked about. Skinner said in behaviorism, we can only study stimuli and behaviors and consequences because we can't look at thoughts. But if computers could be made to model thought, then maybe we could look at thought, because you can look at a computer program and you can experiment with a computer program, which you cannot do, obviously, with human thought. So that was the first thing that happened, that began the cognitive turn or the cognitive revolution. The second, one of the big second things that happened is a man named Noam Chomsky, who you probably know. He's still around, he's still talking. In 1959 published a devastating critique of what B.F. Skinner had called his most important work, a book called Verbal Behavior that he had been working on for 20 years and finally published in 1957, in which Skinner accounts for the development of language entirely with behaviorist principles. His basic idea is that kids start off making lots and lots of noises with their mouth because it feels good. And so they're rewarded in that way. And then by the responses of people around them, they learn to make the noises that get them what they want. So the first time the little kid goes, Mom, Mom, Mom goes crazy and goes, oh, look at him, isn't he cute? He's saying Mommy. And rewards him with all this attention and affection and patting and everything. And so that's how people learn to talk. It sounds logical, but as Chomsky proved pretty completely in his critique, that's not how people learn to talk. What we do know about how language develops is that language develops in a certain pattern that seems to be across all cultures, which again would stand against what Skinner has to say. And what happens is all babies start off making random noises with their mouths and tongues. It's as though they're trying out their equipment, kind of. They go da da ba ba doo doo doo. We call this babbling. And if you ever go listen to a little 6-month-old in its crib when it doesn't know you're there, that's the kind of noise you'll hear. And then gradually the child stops making the noises that are not in the dominant language that he hears. So the noises drop out when he doesn't hear them. You realize so far there's been no rewards, okay? And then children begin to speak with what we call one-word sentences. All children across all cultures. Obviously the words are different because they're using the word from their sentence, from their culture. But a one-word sentence is a word like up or cookie. They tend to be imperatives or sometimes descriptives like doggy. And the single word stands for an entire sentence. When a child says cookie, he's not merely naming a cookie. Anybody who's ever had a kid knows perfectly well that kid is saying, I want a cookie. And if you don't give it to them, they will say it in increasingly irate tones. Same with up. Okay, then children all shift to what we call two-word sentences, which usually contain a noun and some sort of operator. So you get things like me cookie, or me up, or doggy nice, okay? And again, that stands for a whole sentence. One of the other odd things about how children learn language is that they learn objective pronouns like me and him before they learn subjective pronouns. And if you've ever listened to Sesame Street's Cookie Monster, you know exactly what I'm talking about. Cookie Monster says, me want cookie. No child ever heard anybody say, me want cookie, especially if they haven't been watching Sesame Street. But that's how children start off talking. So Chomsky's theory, which he put forth in his critique of Skinner's verbal behavior, is that children are hardwired to acquire language. That yes, they do have to have a model for language, they do have to have an opportunity to practice language, but it's not all about reward, that there is an innate hardwiring that we're meant to learn. So again, you can see the notion of this computer metaphor kind of arising here. Anyway, so we have the cognitive revolution. And basically, what the early cognitive scientists, the information processing folks, and many, many cognitive scientists to this day are thinking about is they're thinking of the human being as computer. And if you look at any sort of anything about information processing, you will shortly find out that everybody's got a slightly different model. There's a model in your chapter for today. There are models all over the web if you care to check any of them out. The important thing is not the exact elements of the model unless you want to be an information processing theorist. The important thing is that essentially the model is based on a computer and very much parallels a computer, although there are some very big important differences between computers and humans that the information processing theorists all recognize. So here is one model that's a lot like the one in your book, but not quite identical, and none of them will be identical. Don't let that bother you. But here's one that has on it a lot of the things that I like to talk about. So it's the one I'm going to use today. And let's kind of walk our way through this model. First thing we're going to look at is sensory memory, also known, as your book mentions, as the sensory register, also known as sensory input. Now, let's talk about computers and people for a minute. What are the inputs, the sensory inputs for computers? Well, you've got a lot of pictures of them here. You've got disks, you've got a mini cam, you've got a modem, you've got a microphone, a mouse, a keyboard. All of these things input information into the computer. The human being also has devices that input information into our brain. We call them our senses. And even though I have 5 pictures here, they're actually a lot more than 5 senses. But the ones we're most familiar with are vision, hearing, touch, which is really a number of different senses, as this little diagram shows you. Touch is heat and cold and pressure and pain and a whole lot of other things. There are actually specialized nerves that carry each one of those. Smell, which is an amazing chemical analysis factory that you carry around in your head. And taste, which is not as talented as smell, but teams up with smell to identify all kinds of different foods and things like that. We also have an inner ear sense of balance. We have, if you, like me, have recently been ill, you'll know that you have sensors inside your stomach that tell you when it's being bloated or when it's twisting or uncomfortable. So we have a lot more sensory organs than just five, even though traditionally we talk about the five senses. Okay, so let's look at people's sensory memory, also known, as we said, as the sensory register or sensory input. It takes in information from all our senses, many more than five. It has very large capacity. It has very short duration, less than 5 seconds. And it is affected heavily by perception, which in turn is influenced both by neurological hardwiring and long-term memory. In other words, what arrives at your brain from your senses and is recognized by your brain is not reality. It is reality influenced by the limits of our perceptions. For example, we don't see ultraviolet, so ultraviolet light is all around us, but we don't see it, we don't perceive it. Therefore, it never makes it into our short-term memory. And it is also influenced by our long-term memory. So first of all, let's talk about some of the hardwiring. Human beings have certain predispositions in perception, which are there in order to help us make sense of our world and to survive. And one of them is we tend to perceive simplicity as opposed to complexity. We tend to try to reduce things to the simplest picture. For example, if you look at this shapes thing that you're seeing on your screen right now, what would you call that? Think about it for a second. Most people will say something like 2 rectangles, 2 shapes. Nobody says 5 shapes, even though there really are 5 different possible shapes there. But we reduce it to the simplest, the 2. Look at this picture. What would you say it is? Again, most people say it's a line going up and down. We tend to see movement and directionality. Now, is that line really moving? No. Is it really one line? No, but nobody ever says 13 lines. Last one, take a look at this. What's that? Almost everybody says a circle. And by now you're waiting for me to trick you, so you might say a dotted circle. But I've never heard anybody say it's 9 arcs. We tend to, we favor in our perception closure. We tend to fill in the blanks. And it's a good thing we do, because otherwise we wouldn't be able to hear most of what people say, because we don't hear every single sound, so we fill in the blanks. And we wouldn't be able to see at all, because our eyes take pictures like a movie frame, only usually pretty quickly. And it's a movie's a perfect example of this. If you look at each separate frame in a movie, nothing's moving. But when we show them all together, our brain fills in the infinitesimal distances, and we see a picture of something moving. So those are predispositions in perception that we have, that all of us have. There are also some individual predispositions in perception, and here is probably the most famous one. Take a look at this figure. What did you see? If you saw 2 faces, you're the kind of person who tends to perceive the ground, the background of things, the whole picture. If you saw a candlestick or a vase or something like that, you're the kind of person who tends to see the figure, the foreground, not the background. And scientists have been playing for decades with other differences in the way people think. People who tend to see figure versus ground. And if you want to, you can go look up some of that. It seems to be a built-in sort of a difference. Okay, besides our hardwired differences, our knowledge enormously influences what we see and hear and smell. Partly because you have to know what you're looking at most of the time to know what you're seeing. And partly because, again, we tend to fill in the blanks of things. So when we think we're looking at something familiar, we'll fill it in. Here's just a couple examples. I want you to read these partially obscured words to yourself or out loud, whichever you prefer. If you're like most English speakers, you read the cat, and because you're on the lookout for tricks now, you might have noticed that the H in the and the A in cat are actually the same. But you had no difficulty telling that one was an H and one was an A because you know what they're supposed to be. You probably then went on and read red, spot, fish, and det. And you might not have noticed that the R in red and the P in spot are identical, as are the E in red and the F in fish. But again, your mind was in no doubt at all of which they were because you knew what ought to be there. What's really fascinating is that most people read that last word as det, especially if you make them read it quickly out loud. But the third letter there really can't be a B, can it? In fact, it is identical to the D in red. But we read det because there isn't another word that makes sense there. So we kind of change what we see depending on kind of what we think we ought to be seeing. Here's another example. Okay, stare at this deliberately degraded picture for a little while. What do you see? A lot of people will say they see a dog. If you didn't see a dog before, do you see one now? There's a Dalmatian there with his head down. He looks like he's licking at something. Other people will say they see a tree with shade. I have had people who said they saw a cow, who saw a wheel, all kinds of strange things, two intersecting paths. Now that you've heard about them, do you see any of these? It's kind of a fun thing to play with. Okay, so how do things move from the sensory register or sensory memory into your short-term working memory? Well, with computers, we know how that happens. If you move the mouse, it moves by either wireless or by wires, and that's basically how computers do it. We've got this thing called attention that helps us move things, because if you remember, the sensory register is huge. You could register everything in your environment, but you can't pay attention to all of it, and we're going to find out why in a couple of seconds here. So attention is a necessarily limited resource, so interference is very common. In other words, of all the things that are coming to your sensory register right now, you can only move a very few of them into your short-term memory. And as I said, we're going to talk about why that is in just a second or two. So there's a lot of things that your register will perceive, but they'll never make it into your memory. You won't even know they were there. The classic example is a ticking clock. If you own a clock that ticks or hums, think about when you hear it. You don't hear it during the day, even if it's quiet. If you're reading or something, you don't hear it because your attention is taken up. The time that you hear it is when you're lying in bed at night with nothing else to think about. And then you hear this tick, 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 which drives you crazy maybe, who knows? Or maybe you like it. Another classic use of this limited attention is we know that people who have chronic pain actually feel less pain if they have a stimulus in some other way. We can cause people to feel less pain by putting their hand in cold water briefly, or by distracting them with a funny movie or something like that, because their body can't pay attention, as much attention to the pain when it's got something else going on. Now obviously if the pain becomes overwhelming, then it gets all the attention and you can't pay attention to your movie. Okay, so how does attention work? Well, again, there are some biological presets, and these are things which helped us survive as cavemen and still help us survive driving the expressway into Atlanta. And that is, we pay attention to noises, we pay attention to sudden movement, we pay attention to novelty. If you walk into a classroom, you might not notice that Susie's wearing a red shirt unless Susie never ever wears a red shirt, and then you might notice. Or you might not, if you walk into a costume store, you're not going to notice the person wearing the bunny suit. But if you walk into a normal classroom and somebody's wearing a bunny suit, you're going to notice that because it's novel. We also pay attention to contrast. If Susie's wearing a red shirt today and that's not all that unusual, you won't notice it unless everybody else wears white. And then you'll be able to tell me, bang, Susan was wearing a red shirt, because there's a contrast. However, attention is also hugely influenced by habits. We have a habit of paying attention to one thing or another. This is why we can drive. And also by our intentions or our goals. So that if you are trying to read something, you will not be paying attention to some other things. If you're watching this and listening to this, there are other things in your environment that you're not paying attention to. Okay, so I'm going to have you pause at this point and watch a couple of very short videos that illustrate, in kind of a fun way, both the necessity of this sort of filtering activity that attention does, and the disadvantages or dangers when attention filters what gets into your short-term memory. In other words, what you notice.